And we are now on to the next unit, unit 6. Unit 6 is all about thermodynamics. So at the end of unit 5, we started looking at how energy explains rate of reaction. Now we're just going to look at energy in general. Like, how does energy connect with chemistry at all? Okay, outside of just rates. Yes.
I have a general question, but would the 6-7 test be before the end of the thing, right?
So for you guys, we don't have any more tests, combo tests anymore. Now we just have basically mini tests for each unit. Yeah, Quizlets. Okay. Test. Oh, when we so anyway, this marks the 4 or 5 test marks the end of combo tests because of your guys' squished spring semester curriculum schedule. You will now have unit 6 test, unit 7 quiz test, unit 7 quiz test that you will be able to retake for full credit, like a quiz. All right. Before spring break, and then you will have the non-graded but scored midterm for practice for up our units 1 through 7 content. After spring break, we have 2 more units, 2 weeks to get 2 units done. Units 8 and 9, or 2.5 weeks to get 2 units done. And then they will each have their own respective quiz test. And then the final exam occurs right before your AP exam, so that that is graded. That is graded like a normal test. Okay. Yes. And it is supposed to be the final exam for everyone in the class, whether or not you're taking the AP exam, but it's also supposed to be a really good practice round for those that are taking the AP exam May 1st. Okay. After, just so you guys know where we're headed, after May 1st final exam, I will not make you do anything the next day. We will just have like a movie day or something. And then all of May will be spent catching you up on all the labs you did not get to do. You guys need to have 16 hours of lab to complete this course. You have done 3. Okay. So you guys are going to do a lot of labs in May. But the plus side is we have ample days. So I'm going to give you work time in class to complete your lab write-up. So ideally, there's no homework except for the giant organic chemistry project that you will be doing. That will be a heavy homework week for you. Okay. But other than that, that's it. I have some guest people coming in. Unfortunately, not firefighters. I tried last year and I cannot degrade myself to that low level of begging like I did last year for a fraud. And then my little sister will probably come and talk about what it's like to be an engineer major. Okay, so I do have things, but just so you know, that's kind of where we're headed. Okay, we are officially in the second half of curriculum, 2/3 into the first half of your semester. Yes.
Any physicists?
Huh?
Or any physicists?
No, we don't know. Yes.
Just to be clear, for the 6 and 7 tests, would those be retakeable?
Yes. They would be retakeable like a quiz, but they will be larger than a normal quiz. Most quizzes are 10 points. These test quizzes are like 15 points.
And will they, how many would they go?
A normal test is about 20 to 23 points. Yeah. So it falls right in between. All right. So that's your overview, giving you kind of a vision for the last half of, or last 2/3 of AP chemistry. But since we're starting the last half of curriculum, I wanted to give you guys that insight. And you guys, for the warm up, we're supposed to fill in this section in your unit 6 notes. So someone tell me, what's enthalpy? Nora.
The potential energy that's released or absorbed.
Yeah, it's the total, energy change in a system. Okay, and this is technically, we already talked about this, just reworded. And could you say your definition one more time?
I just remixed it. Okay, it's potential energy that's released or absorbed as heat.
Okay, perfect. It's total energy change in a system that is released or absorbed as heat. Perfect. So we have 2 ways that we can write in energy into an equation. I give you the thermochemical format. There's also H notation, and this unit will particularly prioritize H notation where you write it separately outside of the chemical formula. Based on the placement of energy, is this an endo or an exothermic reaction? Based on the placement of the heat energy value. Endo, why?
It's being put into.
Being put into the system as a reactant, okay? So this is definitely endothermic. And what's kind of weird about molar enthalpy values is that sometimes you get non-whole number coefficients and you're like, how do I have half a molecule? You don't. But to make the number pretty, they measure it in lab and then they do it per mole. So they fix the ratios accordingly, even if that means a fractional ratio. And okay, so how would we make this into a whole number balanced coefficient equation? What would this turn into? Could someone tell me?
The 2H2O turns into 2H2 plus O2, and then you double the energy.
So what's the double of 286? 572. Okay, kilojoules per mole. Okay, perfect. Okay, and that right there, by the way, is called a molar enthalpy value. Actually,
Isn't it just?
it's just kilojoules. It's just kilojoules because it's not per mole. It's too many of them. Okay, so it is molar. It is not molar enthalpy. It is just straight up enthalpy. Okay, so notice enthalpy is an extrinsic property that is measured in kilojoules per mole, right? So don't forget, this is going to come into play very soon. This is going to become a very important thing to remember. Extrinsic values, you will soon discover, I can spell remember, you will soon discover, allow us to do some interesting algebraic manipulation as long as with the amounts present. So if we change the amount, right, multiply our reaction, we also change the enthalpy, right? And if we start doing algebraic summation of equations, like we've kind of done with kinetic multi-step, and we have a certain energy that goes with each multi-step, we can find the sum of the energy of the reaction that we want to create. Source of energy, bond energy. What is that exactly? Yes.
Sorry, that was a question over the last.
Oh, yes.
In regards to property,
Yes.
why don't we measure enthalpy almost with a change in temperature rather than a change in energy?
Because change in temperature is based off of particle movement. Temperature is a measure of kinetic energy, but heat is not temperature. Temperature can indicate the potential of heat present, but it is not heat itself.
What's the difference?
We are going to talk about that in about T-1.5 days. Bond energy. What is it? What do you guys define it as?
The energy stored in a bond.
Okay, so it's the energy stored in the particular bond arrangement. And like, if some of you guys aren't even taking notes on this, that's kind of probably fine. Because again, this is Unit 5 review. So we're just trying to get you guys synced up and leading in. Yes.
Why exactly does enthalpy increase when you add energy to bonds rather than the other way?
Why does what?
As in, if enthalpy is an extrinsic property measuring like outside factors, why exactly does it increase when you increase the amount of energy stored within it?
Well, it's not measuring outside factors. Extrinsic just means it's dependent on amount present. It's not like external factors.
So how can it be dependent on the amount present if it's also measured in kilojoules per mole?
Because of the per mole part. If we now have 2 moles of it, now it's not per mole. Let's just like we did with the thermochemistry goal.
Well, we have 2 moles of something kilojoules per mole.
So it's not per mole anymore.
But it is. It's just 2 moles.
But we doubled the value. The value doesn't stay the same. The ratio stays the same, but not the value itself. The magnitude changes. Yes, please do.
None of the keys match.
We tried to make that.
So you sat there and loomed over my shoulder. What do you mean we? Okay. Okay. So another thing you should recognize is bond energy. Well, you guys got introduced in the, remember that what was that curve called? Potential energy curve, right? where you had bond, we say there's like a distinct perfect like bond length, right? Bond energy can also be understood as the energy required to break a bond. You could look at it from the reverse. Okay? You could look at it as the energy required to break a bond. That's like kind of another way of looking at it. So it's an indication of strength, right? Indication of strength of bond. The higher the bond energy, Be, the stronger the bond, the more stable it is, right? Higher the bond energy, Be, the more stronger it is. Yes.
I'm sorry, I think this is a question for like multiple units ago.
Okay.
But why exactly is potential energy active and not zero?
Ah, because the universe loves the release of energy. The universe loves more stable arrangements which release energy out into the surroundings.
Isn't potential energy being zero the ground for what defines the stable?
From a physics point of view, not from a chemistry point of view. Yes.
So from a physics point of view.
See, we need to stop with these physics questions, okay?
So like in, there's obviously like the strong force between
Yep.
nucleus together, right?
Yep, yep,
And be like energy to break that.
yep, yep.
Is that similar to breaking chemical bonds? Is it like the same
Maybe. That's a really good question. I don't actually know if I can answer that confidently. Remember, it's really a lot about collision. So it's almost it's a physical force being applied through the particles themselves colliding. But yes, you would definitely have to the interaction of the nuclear strong force would definitely be at play because you are also having the tension is created through the nuclei attraction cross atom. So I assume there would be an element of that to be true. I don't think it would be the primary though. I would not find that reasonable. Yeah, but like the way that the nucleus, having the nucleus is being dependent on that affects how bonds are attracted and formed too. So I would imagine that you could argue that was an adjacent impact. Just wouldn't ever say that. I don't think a chemist would ever describe it like that. Yeah. So types of chemical energy. Okay. So let's just get clear on some of this. We have multiple types of chemical energy. The first is electronic energy. Okay. And just by the way, chemical energy can also be defined as the sum of various types of chemical energy, such as below. Sum of various types of chemical energy is also defined as chemical energy. Just so, I don't know why the textbook found that's like super important, but like whatever. Maybe I'll delete it next year. Who knows? Okay, so type 1, electronic energy. And trust me, I tried to get rid of this section for you guys, but it's definitely in the manual, even though I have not seen a single question about it. It is in the current manual. So electronic energy is the type of is the subcategory of chemical energy that is based off of the kinetic energy of moving electrons. All right, due to electron nuclei, okay, attractions, aka nuclear effective charge, ZEF. Nuclear effective charge. Remember, nuclear effective charge is the preferred understanding of Coulombic attraction for the AP. Anytime that you talk about comparing like trends between two different atoms, you really need to include nuclear effective charge. The nuclear effective charge has weakened because there's more energy levels, therefore more electrons blocking the outer valence electrons. The nuclear effective charge has increased for this atom because there's more protons creating a larger pull. Like nuclear effective charge is a winning phrase for the AP. ZEF, Z subscript F, A, F, E, F, F. Yes. Well, Coulombic attraction is general positive, negative, anything. But nuclear effective charge is the chemistry application of Coulombic attraction. Coulombic attraction can go with anything, physics, all that. I mean, they won't count you off, but like, it's just more like they like the nuclear effective charge. Okay, the second type of chemical energy, okay, is rotational energy. This is all in addition to bond energy, by the way. This is like all in addition to bond energy, okay? Rotational energy is the result of the kinetic energy due to, okay, rotational motion around the center of mass. That could be relative to the individual atom itself or the entire molecule. This is very physics for me. I don't ask me any more questions. Like I'm just telling you what you need to know. Okay. Vibrational energy. Okay. This is the energy due to, okay, the vibrations. Kinetic energy due to vibrations of atoms in a molecule. Atoms are always shaking it, guys. It's pretty exciting. Okay. Yeah, I don't know. I got some conflicting feedback from kids being like, I think we discovered it. And I was like, I'm pretty sure we haven't, but like maybe. If we did, it was like a one-time shot after like $2 billion worth of experimentation. Like, okay. Translational energy is the kinetic energy associated with movement of gas molecules. Whoa, baby, what was that about? Of gas molecules. So translational is literally the movement of molecules side to side. Like a person scanning you. Yeah.
Would you say that we need to know Jesus Ward realistically, or do we need to know?
Apparently, you need to know all of them according to the AP manual. I have yet to see a single question, but the AP manual says you should know that these exist and what they include.
You haven't seen a single film on any of them, right?
I haven't seen a single question on any of them. But like, and neither have my students taking like Princeton review. Like Kyle did like a whole Princeton review book. Didn't see a question on it, I don't think. Yeah. So I don't know why it's on the manual, but I am legally obligated to teach you it because it's on the manual. I mean, according to the AP College Board, that's what I'm supposed to follow, the curriculum. So let me clarify something. We have bond energy, which is the potential. It's a potential chemical energy, right? And then you have these kinetic chemical energies, okay? So these are all kinetic based, yes. So what we would then say is, okay, we have all these types of chemical energy, potential and kinetic, and here's a little diagraphic, okay? You got bending, and when they bend, they literally flap their wings like this. We can see molecules like creating waves that represent a pigeon flapping. And then you've got symmetric stretching, a little shimmy, shimmy, okay? Actually, low-key, that one is the kind of torquey one because when it stretches, it like pops, okay? And then you got rotational, okay? And then you got translational, up, down. It's just across an axis. It's like, boom, 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 okay? That's all you need to know. So together, the sum, okay? The sum of various types of chemical energy is also known as the total internal energy, represented by E, or in physics, I believe it's U. In physics, total energy, I think, is U. Yeah. And you know what, guys? I think I actually meant to write this definition down here. Copy, paste. I think I definitely meant to write this definition down here, guys. So
nothing up there.
Just kinetic energy. Those were different types of kinetic energy for different types of kinetic energy. Sorry, guys. I see that I misread my notes. These are different types of kinetic energy below. Different types of kinetic chemical energy below. And then total internal energy is the sum of various types of chemical energy, which includes potential and kinetic. I apologize. That was 100% my fault. I apologize. What does it say? Oh, I see. Let's see. I may not know exactly how you feel, but I care and I cannot listen right now. I'm looking at this like input of how to apologize better. I can see you're feeling frustrated right now and I want to acknowledge that. Okay. So, so thermodynamics. Thermodynamics is the study of, this is unit 6 now. That was all kind of intro. So what is unit 6 about? Well, unit 6 is the study of these energy changes between these energy forms. Okay, study of energy changes and the laws governing, okay, and the laws governing the conversion of heat, enthalpy, into other forms of energy. Thanks, Julian. Okay. Boys, I can just take that up to the tennis games. You can leave that pack for me. I'll do that. So, just like a little terminology for you, we call a state function or a state variable, because we're going to look at several different characteristics or properties under thermodynamics. And so we call a state function any property that only depends on final versus initial. Versus initial state. Where is my TA? She just like, but she not walk. I like heard like a fumbling and then I saw her like leave. Final versus initial state. So a really good example of this is enthalpy. Like enthalpy is a very important function or variable that we look at for understanding studying thermodynamics, because it's heat. And it's a state function. When you calculate the enthalpy of a system, it's products minus reactants. Like we don't actually care how it happens. We don't care anything about the activation energy. All we care is about what's the difference between final and initial. That's a great example of a state function that's pertinent to our topic of thermodynamics. Okay. So, and when I said AKA, another way you can think about it is it's independent of pathway. Where'd you go, buddy? You okay? You doing good?
Oh, yeah.
Oh, that's understandable. I almost peed my pants earlier today. I was dying. Okay.
People like listen to me. One day some poor kid is gonna need like some kid who's from like Pennsylvania is gonna need extra help when his AP Chem is gonna stumble upon.
Trust me, no one's gonna watch my AP Chem videos from Pennsylvania. Okay, they got wicked smart teachers over there. I am just a somewhat smart and slightly enjoyable socially, more entertaining than needed be teacher that does care a lot, who has got a big heart. Okay, that's what I am. So, sign value, right? So with state function, sign value represents, okay, direction of heat flow. Or another way of putting it is heat transformation, heat flow or transformation. So the big idea here is that your pluses and minuses matter. That's like the big idea, is that with state functions, pluses and minuses do matter. Now, on the other hand, the antithesis of this, or the opposing version of this, is a pathway dependent function. And that's a property that does depend on pathway or mechanism. Does depend on pathway or mechanism. So like, for example, work and heat are two okay, that do depend on pathway. And if you're like, wait a second, isn't enthalpy heat? Ew. So there's actually two categories of heat in chemistry. There's enthalpy, which is like the total heat of a system of a chemical reaction. Then there's heat in the specific terms of heat flow, which we actually give as Q. And that's a different heat, but it is called heat.
The way there's like multiple heat systems.
And then of course work is W,
Like, there's just
but like lowercase w. Because capital case W is not the same. Capital case W is tungsten. Capital, capital letter W
capital letter W.
is tungsten. Okay.
Pennsylvania's 37th the nation of education, so they actually need it.
Oh, maybe I'll move to the East Coast.
It's really outward this semester, and so I'm getting some help and feel like that.
So, thanks.
Go
So,
through every lecture, like every
So-
student, like,
first law of thermodynamics. Guys, we have to get through. Woo, we have to get through 3 pages, guys. Come on. First law of thermodynamics, okay, is, I don't even know if you have to write this, but like energy can neither be created nor destroyed. Then don't write it. Can neither be created nor destroyed, but can be converted, aka the law of conservation of energy. Well, not me, I'm from China, so yeah. Mechanism, aka law of conservation of energy. I don't know. That's what the doctors are trying to figure out. So, okay. Common methods for energy transfer in general, okay? That can often is associated with energy conversion. Like oftentimes when you transfer or convert energy, they go often hand in hand. Okay, so I think I repeated myself. Heat and work. Hence why I mentioned them in the first place as functions that we're going to analyze. Heat and work. And this time it's heat Q and work W, not heat H, enthalpy, okay? And so what we say is these, okay, if you have a symbol of positive for heat, you know that heat has been absorbed. I do not disagree with them hushing you. If you have a negative, you know it has been released. And let me just clarify something. This is all within the perspective of the system. This is all from the system's perspective. Maybe it's a better way. Okay. So if on the other hand, for work, if I have a negative symbol, that means the system does work on the surroundings because energy is out of the system. And if I have a positive symbol for work, that means the surrounding does work on the system itself. So energy input. Yes.
Doesn't heat act in the same way as enthalpy in this concept?
Often, yes, but there is technically a place where it differentiates. But for your guys' learning purpose, it will be questioned and answered as if it's the same. But there is a differentiation when you get to higher levels, okay? But I do technically have to teach you that there is a difference. And you're gonna see that being reflected in some of the equations, why we use H for enthalpy calculations, but we use Q for other calculations. It signifies that there is a difference, even though in our context, they often are treated the same because of the conditions around them.
Are they just both representing heat, but in different ways? Like,
Kind of yes, kind of no. I'm gonna leave it at that, kind of. So I should add up here that notice the direction, the sign also matters here. For these pathway dependent functions, they also matter the sign, but the mechanism is a huge influence. So while sign matters for both of these pathway versus state function variables, what makes the big difference is that there is an assumption that you can transform the value through the mechanism itself. for pathway dependent. For enthalpy, you changing the mechanism doesn't change anything in the end. Yes. Okay. So let me write this little note. You can change. That means you could change work or Q via mechanism. It's kind of like the big takeaway for why we care about it being pathway dependent. Okay, so what's the equation that puts this all together, the two energies? Bye, Kyle. We can say that then total energy, internal energy, E or U, in chemistry we use E, is equal to Q plus W. The total change in energy of a system is equal to Q plus W. Okay? Which could be written as Q plus work in physics, negative change of P, negative P times change in V. Pressure and volume, where P is the external pressure.
It's like the isobarometric and isovolumetric.
Maybe. So, this derivation or version of this equation would be only used for a gas system. And then we also have another derivation that manipulates the phone, that manipulates the ideal gas law as well. Okay. So I just want you guys to do this problem because I don't think this is a crazy problem for me to walk you through. So go ahead and try it. So you have this whole potato cannon. Congratulations, you made a cannon with a potato. The fuel performs 948 joules of work on the potato. That's a weird way of thinking about it. And the heat, okay, and it heats the cannon with 1,355 joules of heat. So the question is, what are we saying is going to be the system, or what's going to be the like perspective that we're going to take on? Who's going to be the kind of reaction system that we're analyzing? Is it the potato or the cannon? So for us, we're going to say that the reaction is the fuel, the burning is the system. So if we say that fuel performs 948 joules of work on the potato, okay, then we would say, then we would say if the fuel of the cannon is going to be our system, we're going to go from the system perspective always, okay? That means work is going to equal negative 948 joules because the system's doing work on the surroundings, the potato. Do you guys know what Mr. Potato Head is?
Yeah. Yes. Of course we do.
Oh, of course you. I don't know. I've said a lot of things before that you guys do not know. And I'm like at a loss. Okay. I'm not 10 years older than you. I am 7.5, 8 years. Actually, wait, how old are you? I am 10 years older than you. I'm a decade older than you. Gee willikers. Okay. So, and then from the systems perspective, okay, we see that it releases 1,355 joules. So it's negative heat release from the fuel systems perspective. So then our total internal energy is Q plus W, giving us a value of negative 2,303 joules. Okay. The biggest trick with these problems is getting the right sign. And honestly, I don't see too many of these. I think that might be an MCQ, if that. Because from the systems perspective, work is done, so it loses energy. The system does work on the potato. That's
like exerted energy.
Yes, kind of. It's a little hard to say that there was any distance covered here, but it is more, think about where the energy goes. Okay. Yeah, it's usually from the reaction that's happening. Like it's usually the reaction. Yeah, so it's from the perspective. Okay. All right. So there's one other derivation we can have for this, and you could also say that energy is equal to Q minus change in nRT, because technically, according to ideal gas law, PV equals nRT. So if we said that the system for a gas system is work is equal to negative P times change in V, well, we could also say then that work is equal to negative change in nRT. That's just like your ideal gas law variation. Okay. Again, this does not tend to be a super highlighted topic. Watch this, like this year, they're just gonna be like energy. But they could screw you over. I don't know. Like they can do whatever they want. But I haven't seen any questions that really dig into this deep. Boys, do you remember if there was any questions where you used internal energy and the AP? I don't think so. I can't think.
This is mainly preliminary to.
You know what? If Keaton says there wasn't that many, then there wasn't that many. Don't ask Kevin if he remembers anything, I'm realizing.
Kevin doesn't even know anything.
Okay. So, some tips to consider. This is where I clarify why we often treat heat and enthalpy the same. Okay. When heat Q is exchanged between B/W, system and surroundings, SURR is surroundings, and external pressure is constant and pressure is constant. So like whatever that pressure condition is, as long as it stays constant, then Q equals enthalpy. And that's what most of your problems are assuming, that pressure is constant. Then Q equals H for enthalpy. I think you need glasses
+5.
or not a hat brim.
+5 what?
Surroundings,
Oh.
not slur. God.
Hey guys, if you can bring some binoculars and then look at the screen.
They actually, you are so rude. So rude.
Joy, did you give
Do
me
you
a-
hear this child over here? Okay. Tip 2.
I'll bring a telescope.
Okay, for reactions.
Handwriting decipher in there somewhere so you can actually read the writing.
Not for reactions not involving gas
You can close captions for me.
or change in moles. Work equals W. Work equals 0. Like W equals 0. Work W equals 0. So the overall internal energy will equal the overall enthalpy. So go ahead and try the sample problem below. So for this problem, you should have, you were asked, how do Q and H compare under these circumstances? Because it's constant pressure at room temperature in an open container, assuming constant pressure in the environment. What we would say is that A or I, Q is equal to change in H. So calculate the change in internal energy. Okay. Well, what we would say is that the internal energy for II is equal to Q, and I'm going to use the derivation of change in nRT because based off the information I'm given, that's all I got. Okay, where here R is going to be 8.314 joules per moles Kelvin. Kelvin? Oh God.
So we'll be better at Kevin.
The amount of K names in my life, geez. Huh? I don't know, man. Make the judgment call. Okay. So
Just give
what does the AP say? Oh, then probably not.
Just give it. Just give all the points.
Oh, the answer key show it, then it should show work.
Give all the points.
So then what we get is this is equal to, we get that we're given enthalpy, but we're told that in this condition, enthalpy is Q. So it's going to equal 571 kilojoules minus change in nRT, which is 1 mole, times We're gonna convert this to kilojoules, so 0.008314 kilojoules per moles times Kelvin, gee willikers, okay, times room temperature is 25 degrees Celsius standardly. So we would say that it's 298.15 Kelvin, so that all of our units cancel out. And we would then get that this is equal to 569 kilojoules per mole. Not too bad, not too bad. It's just math plugging. So,
Where'd you get 0.08?
because I converted R from joules per moles per Kelvin to kilojoules per mole per Kelvin.
Where's R?
You said
Where's
that
R
again.
represent?
R is the ideal gas law constant.
Oh, it's the R constant.
Yeah.
But is that in our equation sheet?
Yes, yes.
Why can you do that? Because you wrote delta nRT and then you just calculated nRT. Does nothing change as far as I can tell?
Oh, well, okay, so change is an interesting way of putting it. It's for the system, and you're technically measuring the system based off of, that's a really good question. It's a really good question. It is arguable you do not need to put that change. It's kind of like what, it's like, okay, so when we, you know what, I'm gonna ask you to pause because I think you're gonna see a similar scenario when what I'm gonna introduce next. And it's based off of the conditions that you're measuring the interactions relative to a condition, right? So that's a really good question for this one, because it makes more sense for the next type of enthalpy calculations I'm going to do that we would keep change. This one's a little harder for me to explain. So I honestly think that that was a great question. I do not have the capacity or desire to answer, like to put much time into answering that question. But I do know that this is how they write it in textbooks, that this is the derivation from that. Because of work, it has to be because I think this is my answer. Since work is defined by change in volume, to make this equivalent to this with the ideal gas law, it has to be under the condition of change. So that it becomes P change in V equals some change in nRT.
Right, but we saw no change.
Yes, but technically for it to be equivalent to work, there has to be change as well.
But wouldn't the change that there's zero change, right?
Yeah, which is also why I think you have a really good question, but this is still the formula you would use. Oh, I think that's the winner. Get it, Jay. Okay, so yes,
It adds up to 9 and 11.
okay.
So-
I put it on the, yeah, that's why I also am concerned about their grading.
So just leave.
So it has to be out of 9 and 11. I don't know if they did it right. And I also don't know if they made the judgment calls correctly. I'm sorry. Okay, so let's talk about how we calculate enthalpy now. My hair's caught on my earring.
Oh my
How we
God,
calculate
so
enthalpy.
much.
Okay. This is kind of like a different subtopic within. We're now moving on from total internal energy to just enthalpy. So first and foremost, you need to recognize that we tabularize data. We test things under, this is very stuck. We test things under the same conditions so that we can create a table of data values to make comparisons between processes or compounds. Okay. And so those conditions that we tend to test things under are known as standard state conditions. And standard state conditions is defined as the state, as in solid, liquid, gas, right? Solid, liquid, gas. Okay. An element exists under conditions of convention. And that convention for us is 25 degrees Celsius or room temp. Pressure being equal to, external pressure being equal to 1 atm. And for any liquids or gases, having a 1 molar solution. Okay. I don't really know how to get my hair out of this earring. So why do we like this? It's because it allows us to standardize measurements for calculating the H enthalpy of a system. Okay. It also allows us to compare, right? If we can standardize, we can also compare, which is really helpful, right? So we do this with enthalpy calculation. So we're moving on again from internal energy now, looking specifically at the state function enthalpy that's dependent on final versus initial, reactant versus product status. Okay. So instead of just calculating enthalpy in general, we can actually create a tabularized data of enthalpies distinct for a particular reaction or distinct for the formation of a particular species. And we can use algebraic summation to then piece together a desired reaction and determine its enthalpy. Yes.
And just to be fair, because we have a fixed temperature and a fixed pressure, that does mean that enthalpy is equal to
Q.
No.
Technically, but we would still write enthalpy H for these equations. If you write Q is equal to Q of reactants minus Q products, they will count you wrong. Because all it's saying is that it acts as the same. It's quantified or treated as a number same, but it's still a different concept, technically. Okay. So enthalpy of formation is the heat of reaction for a chemical change involving, or maybe the word is based on, the heat required to form the respective compounds from their constituent elements in standard states. In standard state conditions. Okay. So this is going to make a lot more sense when I introduce Hess's law. Like, how do we even use this? Because right now, enthalpy of formation is just like this object that is a number that represents something about how we collected the number. Okay. Hess's law puts it all together. So Hess's law, and you're going to have AP walkthrough on this. Hess's law is known as, it's a method. Joy can put them into my grade book. Meth is them, and Joy, put it in the comments on your computer you want to do to Canvas, because you're going to put comments and then you're going to total up their scores because they're for the FRQs. Yes, thank you. Was that Kevin's? Yes. It's the method, a method. It's one of many methods, okay, for calculating change in heat for a system based on the summing up of the heat of formation values for the respective or for the chemical species involved in reaction. Okay. It's kind of another algebraic sum thing. Can I read the equation? It's that the enthalpy of the system is equal to the sum of the enthalpy of formations for the chemical species involved in reaction. So we like this because it allows us to ignore the mechanism, right? Here we're working as a state function, AKA, right? We are doing state function calculations. We're ignoring mechanism. All right. Yeah. And under a set of constant conditions, right? constant conditions or standardized. I keep on using the word standardized, but that's why it's so important because it's all standardized. Standardized conditions. So let me show you how it works. So here we have heat of formations for respective CO2 and H2O. And then we have a general combustion reaction that we also know the heat enthalpy of. And together, all three of these are going to somehow help us total up to this net reaction. We're going to somehow construct this net reaction from these three reactions. So Hess's law is the method. This is the method. Hess's law, what I'm about to do is this method. So what happens is if I want to get CS, I need to find it. So I see that CS in my net equation is found on the reactant side for the second equation. H2 is found on the reactant side in my third equation. And CH4 is found on the reactant side in my first equation. So somehow I need to arrange these equations in such a way that give me my net reaction that I want. So automatically what I'm going to do is I'm going to say, well, I like that C and H2 are on the correct side, reactant side. But what's the problem with H2? It doesn't have enough. I need two of them. So what I'm going to do is I'm going to multiply this entire reaction's coefficients by 2. And if I do that, I'm going to reflect it in my enthalpy because enthalpy is an extrinsic property. It's dependent on amount, right? So I'm going to multiply that by 2. Then that gets me the following coefficients: 2, 1, and 2. Okay. Now, all right, I like that CS is on the right side, and I like the coefficient in front of it. Nope, not going to answer that question. So I'm going to leave that one alone. So that means I don't mess with the heat of formation value. Now I'm going to look at the one above and say, well, I really like that I see H4, but it needs to flip. So I'm actually going to rewrite this as CO2 plus 2H2O goes to CH4 plus 2O2. And if I flip it, that means I'm going to flip the sign value for my enthalpy and say it is positive 891. Thank you. Kilojoules per mole to reflect it. And what I see is when I sum up this set of reactions based off of their formation values and then just one generic reaction value that we know, I get that my O2s cancel because I have 2 O2 on the products and 2 O2 on the reactant side. I get that my CO2s cancel, one on product, one on reactant of another equation. And then I get my H2Os cancel, one on reactant, one on product. And then what all I'm left with is CH4 on my product side, CS carbon solid on my reactant side, and 2H2 on my reactant side. And that did indeed give me my proper desired net reaction. So then what would I say is the heat or enthalpy of the system to make this reaction occur per mole? I would total up. Okay. Plus. Okay. And I don't know why it's in pink. And I would get a value of a positive 891 plus negative 394 plus 2 times negative 286. And I would get a value of change in H for this particular reaction system is negative 75 kilojoules per mole of reaction. And that's why we like standardized values, and that's why we like and have the Hess's method, because it's an algebraic summation process using our extrinsic property of molar enthalpies or heat of formations in general with respect to particular species involved in a given reaction that we want to quantify. Okay. So biggest tip for you in how to write is find first, look for desired chemical species. Step 2, okay. Flip or multiply reactions accordingly, right? So until you get your species on what side you want them on, or until you get them at the proper ratio that you want them at accordingly. And then step 3, okay, reflect all algebraic manipulations to the H values and sum up, okay? If you flip a reaction, you go positive to negative or negative to positive. If you multiply the coefficients, so you multiply H as well. When you sum the individual reactions, you should get your overall reaction. And finally, quick note, you need to memorize this, that the H of formation for any pure element like a diatomic or metal solid is 0 kilojoules. It takes no energy to form it. And that's that for you guys. Yay. So you have an AP problem walkthrough it's like 20 minutes. It is just conceptual, but it's the only time I'm going to go over these conceptuals. It's just going over these types of problems. So good luck, you guys.